Hi, my name is Aman Sharma and I am your mentor for CSE in YourPedia. So in this video, we will be covering NPTEL question bank series. So as you all know, NPTEL is a great source of knowledge and the NPTEL assignments are made by IITs only and they are very relevant to the GATE syllabus. So in this video, we will be taking a question from theory of computation, and the topic that we'll be covering in that is languages, regular languages, context-free languages and context-sensitive languages, and the machines that are used to recognize those languages. So let's start with the question. So let's start our question. So you have been given three languages, L1, L2 and L3. In L1 it is 0 raised to power P, 1 raised to power Q, and there is no constraint for P and Q. In L2, 0 raised to power P, 1 raised to power Q, but there is one constraint, P should be equal to Q. This means number of zeros in our string should be equal to the number of ones. And the third language is L3, 0 raised to power P, 1 raised to power Q and 0 raised to power R, and the constraint given is P should be equal to Q should be equal to R. So the order of elements in our input for this L3 should be, there should be number of zeros, then should be equal number of ones, then after that there should be equal number of zeros. So these are the type of strings that will be accepted by L3. Now the question is, which of the following statements is not true? First statement is PDA can be used to recognize L1 and L2. Second is L1 is a regular language, third is L3 is a regular language, fourth is none of the above. So you have been given four options. Now in order to do these type of questions, you first need to have understanding of languages. What are the machines that accept those languages? What will be the power of those machines? And how the hierarchy of those languages vary. So there was a scientist called Chomsky who gave Chomsky hierarchy. In that hierarchy, he shows what are the powers of each of the machines that we use to accept these languages and what are the subsets and supersets of these languages. So let's see what Chomsky form was. So he gave an hierarchy for the languages. So the smallest set of that hierarchy is regular languages. After this, we have context-free languages, also called CFL languages. After that, we have context-sensitive languages or CSL. Then we have REC, recursive languages, and the biggest set of these, which is also called unrestricted grammar, is recursive enumerable languages. So these are the sets. Regular languages are the smallest set of all these, and if we go in order, regular, then CFL, then CSL, then REC, and then RE. Now about the machines that are so the machine that will be used to accept these languages are, for regular we have finite automata. Now in finite automata, there are two types of finite automata machines, which is NFA and DFA. Now both NFA and DFA have same amount of power. So you can convert any NFA from DFA and you can convert any DFA to NFA. So they have equal power and they both can be used to recognize regular languages. Similarly, for CFL, we have push down automata, also called PDA. Now PDA is also of two types. One is NPDA, non-deterministic finite automata, and DPDA, deterministic finite automata. Now in this case, non-deterministic finite automata has greater power than DPDA. So there must be some languages which will be accepted by NPDA but will not be accepted by DPDA. Now these languages are bigger set than regular languages but smaller than CFL, and these are called deterministic context free languages, and they will be accepted by DPDA. Now for CFL we use linear bound automata. For REC we use halting Turing machines, and for RE we use Turing machines. So the expressive power of these machines is in this order: finite automata, PDA, linear bound automata, halting Turing machine, and Turing machine. So this is the expressive power and relation between the expressive power of these machines. Now if you can see, if a language is accepted by finite automata, so PDA has greater power than finite automata. So if finite automata is able to recognize that language, automatically PDA will also recognize that language. But if a language is accepted by PDA, you have that information that language is accepted by PDA, you cannot surely say that it will be accepted by finite automata or not, because you don't know what will be the language. So if any language is accepted by finite automata, it will surely be accepted by PDA, surely be accepted by LBA, and surely be accepted by Turing machine. But you cannot go backwards. So this is the hierarchy for our Chomsky hierarchy that was given by Chomsky. Now next thing that we need to understand, how these machines work. So finite automata works on finite memory. It has finite memory. If you move to CFL, or you can say PDA, in PDA if you give finite automata a stack, then it will behave as a PDA machine. So finite automata plus stack will behave like a PDA machine. Now in Turing machine or in halting Turing machine, both machines, you have infinite tape plus read write options, and for linear bound automata you have infinite tape but bounded. Now the question we are trying today belongs to this category. You have to find out whether the language is regular, whether the language is DCFL, whether the language is CFL, will it be accepted by PDA, will it be accepted by DFA, and all. So now finite memory. So if you have to make infinite number of comparisons, will it be possible using finite memory? So regular languages, or you can say if you have finite automata, it cannot make infinite number of comparisons. But stack, if you have stack with it, you can make infinite number of comparisons because you have stack to compare. We will see in some time that how stack does those infinite number of comparisons. So one thing that we need to understand is finite automata cannot do infinite number of comparisons. If the number of comparisons are finite, then the finite automata will be able to do it. But if the number of comparisons, you can say, is infinite, then it will not be able to do. Then we need to have stack. Now after that, if you have infinite number of comparisons, but you have two simultaneous comparisons, then we will see that stack will not be able to do it. With one stack you cannot do infinite number of comparisons if you have two comparisons going on simultaneously. So let's see how our question how to approach our question with this knowledge. So the language 1 is 0 raised to power p and 1 raised to power q. Now in this, number of zeros p and q should belong to n, and there is no constraint on p and q. 0 can come any number of times, 1 can come any number of times. The only constraint is 1 cannot come before 0. If you have number of zeros and after that the first one comes, after the first one you cannot have any 0. You have to have zeros and then ones, and there is no constraint on the number of zeros or number of ones. It can come in any number of amount. So there is a simple DFA for it. First you have to accept zeros. For first 0, accept it. After that you can take any number of zeros. If 1 comes in the starting, move it to trap state. Now after that, when the zeros are completed, the first one you move to next state, and at that state you can have any number of ones, but you cannot have 0 as your input. So this is a simple DFA for L1 language, and if you can make DFA for it, then surely that language is regular language. So one thing that L1 is a regular language. Clear? Now let's move on to the next language, L2. 0 raised to power p, 1 raised to power q, p should be equal to q. This is a constraint given to us that p should be equal to q. Now finite automata will not be able to do this comparison because there are infinite number of comparisons. 0 raised to power p, p can be anything. You have to compare every time you put there is an input for the machine, you have to compare it most number of times. Now L2, 0 raised to power p, 1 raised to power q, p should be equal to q. So finite automata will not be able to make these comparisons because 0 raised to power p, p can be anything. For each input that you give to our machine, it has to make infinite number of comparisons. So you need a stack for it. So if you need a stack for it, it should be accepted by PDA. How the stack will work? There is a stack. Let us say there is an input 0 0 0 1 1 1. For each input, for each 0, we will push 0 into the stack. For first 0, we will push 0 0 0. Now after that, when the 1 comes, we will pop each 0 for the 1. So for the first one, we will pop this 0. For the second one, we will pop this 0. For the third one, we will pop this 0. And when our input is completed, if our stack is empty, then what we can say that the string will be accepted, or we can say the string belongs to the following language. Now let us take another example. Let's say number of ones are less than number of zeros. So when you push 0 into the stack, for the first one, it will pop this 0. For the second one, it will pop this 0. Now our stack is not empty. If our stack is not empty, then this means that the string that we put here didn't have number of ones equal to the number of zeros. So this means that this string will not be accepted in this language. Again, if we take number of zeros less than number of ones, for this, if you put 0 here, 2 zeros, for the first one, this 0 will be popped. For the second one, this 0 will be popped. Now for the third one, we do not have any 0 to pop. So what we will do, there is no command for this. If there is no command for this, our machine will not go forward from this. So if it is not moving forward, then our input will never be completed, and if it is not completed, then it will not be accepted by our language. So this is the way how stack does infinite number of comparisons. Now in this case, there is only one comparison that you have to make, p equal to q. So again, L2 cannot be done by DFA or NFA, or you can say finite automata, but it can be done by PDA. So it is a CFL language. Now let's move on to the third language, L3. You only have two options for stack, pop or push. You can do these two operations only on stack. So let us take a stack, one stack. Let us take an example 0 0 0 1 1 0 0 0. So if you have to count, you have to push some zeros in here. So let us assume we push these three zeros here, 0 0 and 0. Now for 1 you have to compare these ones with 0. Now how can you compare that the number of ones were equal to the number of zeros? You have to pop simultaneously. That's how you can compare the number of ones were equal to the number of zeros. So if you pop these, number of ones are equal to number of zeros. But what about these zeros? How you will be able to compare this? The stack is empty. You don't have any past record of the number of zeros. So, and also you have only one stack. So you can do push or pop. If you don't pop these ones, they will not be able to see whether the ones were equal to the number of zeros. But if you pop these zeros for these ones, you don't have any method to compare these zeros. So either you can compare these two or you can compare these two. There is no such method using one stack that you can compare all three of these elements. So what we can see here is, if there are two simultaneous comparisons going on, then one stack will not be enough to perform these operations. So this language is not context free language because it cannot be recognized by a push down automata, because there are two simultaneous comparisons going on in this. You can make infinite comparisons, but the number of comparisons should be one. If there are two simultaneous comparisons going on, it cannot be done using a single stack. Let us take another example, and in this case we will use two stacks. So here 0 0 0 1 1 1 0 0 0. What we will do is, for the first 0 we will push 0 here. Zeros are pushed. For the 1, for each one you pop a 0 here and you push a 1 here. For the second one, pop this one, enter 1 here. Pop this 0, enter 1 here. Now when these zeros come, they will make comparison with these ones. So for this one they will be popped, and you can say that it will belong to this input will belong to this language. So when you use two stacks, it is a type of linear bound auto-beta mechanism, and the language will be CSL. So the first language was regular language, the second language was DCFL language, or you can say CFL language, and the third language is CSL language. So let's see our question. What was it? So our question is, push down automata can be used to recognize L1 dot L2. Now L1 is a regular language, so a finite automata can recognize this. Now push down automata, we have seen push down automata has greater power than finite automata. So if a push down automata, if a finite automata can recognize this language, push down automata will also be able to recognize this language. So this is true. L2 we have seen is a CFL language, so obviously it will be recognized by PDA. So the first option is correct. We have to find out which of the following is not true. Now the second option is, A option is correct. Second option is L1 is a regular language. Yes, L1 is a regular language, we have seen that. So the second option is also correct option. Third option is L3 is a regular language. We have seen that L3 was not regular language. In fact, it was not even CFL language. It needed two stack to do these comparisons. So it was a CSL language. So this option is here is not true. So if you have to see which of the following statements is not correct, C option is not correct, that L3 is a regular language. L1 was regular, this is CFL and this is CSL. It was done using finite automata, it was done using PDA, and it was done using linear bound automata. You can practice this yourself also and try to remember Chomsky hierarchy. It is very important. If there is a question regarding type of language, or you can say type of machine that will accept that language, Chomsky hierarchy is the only way to do that. So you need to remember and understand how Chomsky hierarchy works and what are the power of the machines that we have studied. So theory of computation is a very important subject for as far as GATE is concerned, and it carries a lot of weightage, around 8 to 10 marks. So I hope you understood the question, and I hope you understood the concept behind the question. So keep watching. We will be posting a video every week on our channel. Thank you.